Hi everyone, I'm Dingding Tsai from Danbury University in Finland. Here I'm gonna introduce our work for estimating the 60 object pose from a single RGB image. The 60 object pose refers to the 3D transformation from the object coordinate system to the camera coordinate system. It can be represented as a 3D orientation and a 3D location of the object observed in the image. Most previous methods are either based on the 2D to 3D correspondences to recover the 60 pose using PNP rank like Symmetry-in-Bay, or directly regress the 60 pose parameters using deep networks, such as cozy pose. These correspondence-based methods are usually not fast enough for real-time applications due to the time-consuming PNP rank. The direct pose prediction approaches can ensure real-time inference, but the performance is usually inferior to the correspondence-based method. In this work, we present a method called SC6D. Compared with previous methods like Symmetry-in-Bay and cozy pose, our method can achieve the best trade-off between efficiency and accuracy during inference. Also, our method does require neither the 3D CAD model nor the object symmetry priors during both training and inference. Before feeding the input to the network, we first crop the object of interest from the original RGB image using the predicted bounding box and rescaled to a fixed size. This process can be formulated as a 2D transformation represented by T. A new calibrated camera intrinsic KB can be obtained for the object-centric crop using the transformation. Additionally, we can also obtain a 2D positional encoding map M by back-projecting the pixel coordinate using the calibrated camera intrinsic. Our network takes the object RGB crop and the 2D positional encoding map as input and outputs the object center projection offset, the object distance distribution, and a 3D orientation embedding vector of the object. The object 60 pose can be then recovered from these outputs. For symmetric objects, the main challenge comes from the fact that different 3D orientations often lead to the exact same visual observations about symmetries. Due to the one-to-many mapping, we can't directly regress the object's 3D orientation parameters from the ambiguous observation during training without knowing the object's symmetry priors. To tackle this challenge, we know a representation vector for each 3D rotation sampled from the SO3 space and use these learned representation vectors to construct a rotation codebook. Then the object's 3D orientation estimate can be retrieved from the codebook by matching the object visual embedding with the most similar 3D rotation embedding in the feature space. By doing so, we can implicitly handle the object's 3D orientation ambiguity for symmetric objects, for example, by mapping all symmetric 3D rotations into similar representations. For estimating the object's 3D location, we separately estimate the 2D projection offset of the object center and the object distance distribution along the z-axis from the object-centric crop. The object actual 3D location can be recovered using these predictions and the calibrated camera intrinsic. We evaluate our method on 3 benchmark datasets according to the BOP challenge. Our method obtains state-of-the-art performance on the challenging TLS dataset without using the object's 3D model and the prior information of symmetries. Here, some examples are shown to visualize the learned distributions. As you can see from the picture, for an asymmetric object, the predicted viewpoint probability distribution only has one peak near the ground truth object viewpoint. For this object with 2 discrete symmetries, the viewpoint probability distribution has 2 peaks about the symmetry plane. One is near the ground truth, and the other one is 180 degrees away from the ground truth. For the object with continuous symmetries, we visualize the viewpoint distribution of the top K orientation estimates. As can be seen from the right picture, these viewpoints are almost uniformly distributed about the symmetry axis. Here, we show some prediction results from the ICBV dataset in the image. The object's 3D model is first transformed using the estimated 60 object pose and then overlaid on the RGB image. More examples from the TLS dataset are shown in the picture. As can be seen, our method not only can handle the object symmetries, but also is quite robust to the occlusion. Please refer to our paper for more information. Thanks for your listening.